Welcome back to part 1a, where I discuss free fermions on the chain. In particular, I discuss the formulation in terms of creation and annihilation operators. But I start with usual wave function quantum mechanics. So consider, first of all, a single particle that lives on this chain, discrete chain. And then in this case, our electron lives at one of these lattice sites, and from time to time it hops to neighboring sites. But what we have in mind is something like this. So this is the simplest model of a solid or crystal. So here's a periodic potential with many deep minima, and these minima represent atomic sites in a crystal. And then the electron lives mainly at one of these minima, but from time to time it tunnels to neighboring minimum. Okay. So the wave function in this case is simply like this. So instead of usual continuous position variable, we have this discrete position variable. And you can also identify this wave function with a column vector with L components. Okay. And here's the tight binding Schrödinger equation. T is not time. It's a parameter called hopping amplitude. And this part describes the hopping of electron from U, not only electron, of the particle from U to site U plus 1, or from U to site U minus 1. Okay, and this is the single particle energy eigenvalue. And I use periodic boundary condition for simplicity. Okay. And then actually, so we describe this wave function as a column vector. Then we can actually rewrite this Schrödinger equation in this form using matrix. So this matrix T is called the hopping matrix, and its entry is defined like this. Oh, here, when I say U and V are neighbors, I take into account the periodic boundary condition. When U and V are neighboring, this takes entries minus T, and it's 0 otherwise. And you can easily convince yourself that this Schrödinger equation is rewritten like this. And then, of course, this becomes this eigenvalue equation of the matrix T. So this phi is the eigenvector of this L by L matrix. Okay. And in this case, it's very easy to write down the energy eigenstates or the eigenvectors. It has this simple plane wave form. Okay, so here K is sort of the name of this energy eigenstate. And this K takes value in this set. It's called a wave number, and it takes value within 0 and 2 pi. More precisely, it's like this. And it satisfies this condition. E to the IKL is 1. Okay. And then if we simply substitute this into the left-hand side of the Schrödinger equation, so this is the left-hand side, and if you plug this in, then it's like this, and then you can pull this part out, and then you get this thing, which is independent of site U. Okay, so you have seen that this satisfies Schrödinger equation. This is psi UK itself. And in this case, here you have the energy eigenvalue, so it's this. And if you plot this as a function of K, you get this familiar cosine dispersion relation. Okay, and of course, this thing can be written in the vector form like this. So of course, this psi is a vector form by this. Okay, and also it's standard and easy to find out that this psi's satisfy this orthonormal relation. This is a computation, but I think many of you are familiar with this. And this is the this is the definition of the inner product I used here. Okay, is everything clear? Okay, that's for a single particle. Now I want to go to many particle case, still using the standard wave function formalism. Okay, now let's consider two particle case, and then the wave function have now two position variables. But in this case, in order to describe the symmetry of fermions, or actually, I have to say that these two fermions are identical. Okay, so we are discussing the system of identical many fermions. Okay, and since two fermions are indistinguishable, this thing and this thing represent the same state. But in this case, you have to have this minus sign in order to describe fermion. So in short, wave function changes its sign when the labels of two particles are exchanged. So actually, in principle, you cannot distinguish between the two fermions, but you have to sort of label. So you call this the first particle, this goes second. But here you sort of change the labels. Then you have to have this minus sign. Okay, and it's essentially the same for n particle case. So the n particle wave function has these n position variables. And then if you change the labels, that means if you apply any permutation to the set from 1 to n, and then you have to have this symmetry relation where this denotes the parity of the permutation. I think you're familiar with this. And now in this case, the Schrödinger equation for free fermions, free, in this case, free means non-interacting. If there's no interaction between particles, then the Schrödinger equation for many n fermions looks like this. And this is basically the same as this single particle Schrödinger equation here. Here you have this hopping to right and left. And here the same thing, hopping to the right and to the left. But here we have many particles, so you have to sum over these labels of particles. Okay. Now, again, it is standard to write down energy eigenstate and eigenvalues for this Schrödinger equation. And I just write down the answer. In order to get energy eigenstate and eigenvalues, you first have to pick these case. Or suppose that so you have n particles, n is given. Then you pick n elements from this set of wave numbers. But in order to avoid a double counting, you just order them like this. And then this is the name of the energy eigenstate, and these are position variables. And this is explicitly written in this form, which is called the Slater determinant, because it has the same formula as the determinant of an L by L matrix. And here, these cases are here. So you have the single particle wave function for the wave function for single particle energy eigenstate. But here you are changing these labels. And actually this is a bit tedious. So you first label particles, and you consider this product of single particle energy eigenstate, but then you change labels in all the possible n to the factorial ways, and just sum them up, just taking into account this phase factor, and then you normalize. Okay, so this is very tedious, but since fermions are indistinguishable, you must do this if you stick on this wave function formalism. And we're going to see that if we use creation annihilation operator formalism, then we can treat exactly the same thing in much simpler way. Okay, and anyway, this energy eigenvalue, this is simple, So we had these things. So this is simply the sum of energy of each particle. So we have n particles, and they have wave number k1, k2, dot, dot, and kn. So each of them have this energy, so you simply sum up. Okay, this is simple. Okay, is everything clear? Okay, so this is about wave function formalism. Now I go on to introduce creation annihilation operator formalism for many fermion systems. Okay, the same thing, but different formulation. And so I just define these operators here. So Cu is the operator that annihilates a particle at site U. And this is its conjugate. And then it can be interpreted as an operator that creates a particle at site U. Okay, and we assume that these guys satisfy something called the canonical anti-commutation relations, which looks like this. For example, so this is 0, but in case of U and V are the same, and then this Cu is the same as twice Cu squared, right? And it is 0. So this means that Cu squared or Cu Dagger squared are 0. And if they are different, then if you switch two of them, you get minus sign. And this tells you that when U and V are the same, and then C Dagger, and if you change the order, then of course you get minus. But since we have Kronecker delta, you get extra 1. Oh, I'm sorry. When I say delta, this is a bit kind of abusive notation. I always omit this identity operator. So I say 1 here, but if you want to be super rigorous, this is identity operator. But I'm going to use this sloppy notation. Okay, so these are the definitions of C and C Dagger. Okay. Now, I also need one more thing, which is a very special state called phi 0, which represents a state with no particles. And we assume that it's normalized. And also, this is a big assumption. So we assume that this C and C dot R can act on this phi 0. Okay? But when CU with any U acts on phi 0, we get nothing. But this is natural from these interpretations. So our interpretation is that phi 0 is a state with no particles, and C tries to annihilate a particle at U. But since you don't have any particle to begin with, you cannot do anything. So you get just 0. Okay. Now with this notation, I can define one particle state. So I just consider this combination. So I operate C dot R to phi 0 and call this U. And we interpret this as a state with a single particle at site U. And now let's compute this inner product. So from this, from usual rule, we see that this should be phi 0 bra CU. Okay, so by using this, this becomes this. And now you have CC dot R. But CC dot R with same U is like this. So this becomes this. But now from this rule, when this acts on this, you get 0. So you only have this 1. So you get this. And from this normalization, you get 1. So this tells you that this state is normalized. Now suppose that U and V are different. And we consider this inner product. Okay, and the same thing, and then you use anti-commutation relation, but here U and V are different, so it's 0. It's simply anti-commute, and then you use this and you get 0. So you see that U and V are orthogonal with each other. That's for one particle state. You can do the same for two particle states. Now for U and V, this should be interpreted as a state with particles at site U and V. Okay, but now suppose that you wanted to have two particles at site U. That's C dot RU, C dot RU, but this is 0 by definition, so you cannot get it. But this is nothing but the Pauli exclusion principle that said that you cannot have two particles in a single particle state. Okay. All right, and now suppose that U and V are different. And then this is a state where you have particle at U and V. But by the anti-commutation relation, this is automatically rewritten like this. So this represents the antisymmetric nature of fermion state. So this represents symmetry of fermionic state. So this kind of thing, rule that you get minus sign whenever you exchange the labels of particle and so on are built into this anti-commutation relation of creation and annihilation operators. Okay, and so the two particle Hilbert space H2 is spanned by all these things, but you don't want to double count, so it's clever to order them like this. Okay, then this exhausts all possible states. And the same for n particle Hilbert space. N is a fixed particle number, and it should be between 1 and L. And then this Hilbert space is spanned by these states, okay, where again we order these U's like this, okay, and you can compute inner product in this space. But to be precise, the inner product in this space, Hn or H2, is actually defined by this relation and this anti-commutation relation. So we assume that phi 0 satisfies this. And we also assume that C and C dot R can act on phi 0 and with this restriction and also with this anti-commutation relation. Then with using all these rules, you can compute inner products of any two states. Okay, so that defines the inner product in this Hilbert space. Okay. Number operator, this is, I think, elementary. So consider this operator, C dot R C, at the same site. And then you will see that this is actually the operator that counts the number of particles at site U. Okay. And first of all, okay, let's look at, this is an easy exercise, but let's look at NU squared. So by definition, this is just C dot R U, C dot R C, C dot R C. And here you have C, C dot R. And from the anti-commutation relation, you see that this is 1 minus c dog c. If you plug this in, then from here you get c dog or cc, that is 0. So you can forget about this part and only plug 1 in here. You get c dog c. So this is nothing but n. So you see that n squared is equal to n. So n squared minus n, which is this, is 0. So this equation tells you that the eigenvalues of n can either be 0 or 1. Okay. Now let's compute the commutation relation, not the anti-commutation, but commutation relation between n and c dog r. Okay. And just plug in the definition, c dog r c and c dog r, c dog r, c dog r c. This is n. But here it's very simple. You get c dog r squared, it's 0. And here you have c dog r c, but this is equal to 1 minus c dog r. And again, c dog r squared is 0, so you just plug in 1 here to see this. And when u and v are different, and then you easily find that they commute with each other. So you get this commutation relation, okay? And c dog r commutation, you get Kronecker delta and c dog r, u. And you also see that since this is this, and you have cu here, if n acts on phi 0, you get 0. But if you interpret this as a number operator, this is very natural. Number is 0. Okay, so now here comes this main part of this observation. So let's consider this single particle state, c dog r u, which I wrote u before. And then in this case, if you apply this nu, then let's do this again. We use this commutation relation. Okay, so this is n c dog r, so c dog r n. But from this commutation relation, you need this extra one. But anyway, if this acts on this, you get 0 from this. So you simply have this. So if you look at this, this state, and if you apply n, you get the same state times 1. So this shows that this c dog r phi 0, which is u, is the eigenstate of n with eigenvalue 1. But very natural. And if you do the same thing for u and v, different u and v, and if you consider this, this commutation relation says that you can simply switch the order, and phi 0 is 0, so you get 0. Okay, so this is only for one particle state, but for n particle state, the same discussion shows you that this is 0 when u is not in this list. In this case, n commutes with everybody and goes here, and from this you get 0. And when u is among this list, and then n commutes with most of them, but when it comes to c dog r u itself, and then you do the same thing as here, and you get this. Okay, that's very easy to see. Sorry, there was something wrong, but anyway, we have derived this relation. Okay, so let me define something more sophisticated. So take any wave function, single particle wave function phi, and then this c dog r phi is a fermion operator that creates a particle in this state. Okay, and by definition, if you take a different state psi and alpha beta complex coefficients, and this satisfies this linearity. And also this c phi is simply the conjugate of this thing. If you consider the anti-commutator of c phi and c dog of psi, and then you precisely get this inner product. Why? Well, you simply plug in the definition, so you have to take conjugate, so you have star and c, and this is simply this, and then this gives you Kronecker delta, so this becomes this, and it's just the definition of inner product. Okay, now it's also natural to consider operators corresponding to matrices. So take any L by L matrix like this. Of course, the hopping matrix is a typical example, and then I define this operator BA like this. Now you have u and v, so we have c dog r u and cv like this. And in this case, we have c here, so if you apply this to this state without a particle, then you get 0. Okay. Now I want to compute the commutation relation between BA and c dog r phi for general matrix A and general state A. Okay, so anyway, let's compute this. So I just plug in the definitions. So this is for this part is for BA, and this part is for C dagger phi. Okay, and now I have to compute this commutation relation. So you just write down C dagger UCV, C dagger W, minus C dagger W minus C dagger UCV. Okay, now here I consider this part, CVC dagger W, and here I use the canonical anti-commutation relation to rewrite it like this. Now consider this part. You just bring this back here, then you have minus C dagger U, C dagger W, C dagger V, no, CV. But you can just simply switch C dagger U and C dagger W to get an extra minus sign, and then that cancels with this thing. So you only have to think about take into account this part. So anyway, this commutation relation becomes this. Good. So you just plug this in here, and then this sum between, so yeah, you have sum over the three sides, but you now only have sum over two sides, and this W becomes V. Yes, W becomes V. Okay. And now let's look at the summation over V. And then this is simply the multiplication of this matrix A and phi. Okay, so this is A phi, the use component of A phi. And then if you look at this, this is nothing but the definition here. So this can be written in this way. So this is a very natural relation. So, you know, these guys, phi and A, they live in this single particle wave function world, right? And now we are discussing these operators that lives in this many particle creation and annihilation world. And but you know, if you take the commutation relation, you simply get this. So this is a very natural correspondence. And similarly, if A and A prime are L by L matrices, and if you compute this commutation relation in this many particle world, and the answer is this. So this is just a commutator between two matrices. Okay, and we're not, this is easy to show, and we're not going to use this in this video, but we are going to use this in part 1b. So probably it's a good idea to sit down and derive this. It's not too difficult. Okay, so now we are ready to write down, discuss many-body Hamiltonian and corresponding energy eigenstates. Okay, and so T is our hopping matrix, and then consider this thing, B hat of T, and call it H. That is our Hamiltonian, and if you plug in the definition, it looks like this. And this is really hopping, right? In this case, you annihilate a particle at U plus 1 and create one at U. So this means particle was at U plus 1, but it goes out and it appears in U. So this is basically hopping, the same thing. Okay, and also note that this is true because, well, this is just a general property. Now let's consider this thing. So phi 0 is a state without a particle. So this is a single particle state in which the particle in the state phi. Okay, and now since H phi 0 is 0, this is the same as applying the commutation relation. But now, by definition, this H is P. So this is the same as this commutation relation. But from what we have seen in the previous page, this is written like this. Now, recall that the single particle Schrödinger equation looks like this. So this single particle Schrödinger equation with this can be rewritten in this form. And this is really the standard Schrödinger equation. If you call this phi, and if you call the same thing phi, and the result is simply this, H phi equal E phi, the very simple standard Schrödinger equation. So this was only for the single particle case, and there is a slight logical gap here, but you can easily convince yourself that many particle Schrödinger equation for free fermions that we discussed in page 3 is written in this language like this, okay, for any n particle states. Now let's write down energy eigenstates for this Hamiltonian. And for this purpose, we shall define the creation operator corresponding to this psi k. This is a wave function for the single particle energy eigenstate, okay, indexed by this wave function. And then I define A dagger k as this operator. So if we recall the definition, this is more explicitly written in this way. So this creates a particle in the plane wave state with wave number k. Okay. Then, since these guys, of course, these are just linear combination, they anti-commute, they anti-commute. And if you consider this anti-commutation relation, then we have seen that this is equal to this inner product. But since we have seen that this satisfies orthonormal relation, so this is Kronecker delta. So this shows that these A operators, A and A Daga operators, also satisfy the canonical anti-commutation relations. Okay. Now, so it means that these are good guys. Now I compute this commutation relation, but it's easy now. So H is BT, AK is C Daga. So what we have seen before, this is equal to this. But now the single particle Schrödinger equation said that this is equal to EK times psi k. So from the linearity, you see that this is equal to this, and from definition, you get this. So this commutation relation gives you this. Very nice. Now we are ready to write down many particle energy eigenstates using this A-R. So to get energy eigenstate, we are first given the particle number n, that it's between 1 and L. Okay, and then you choose n elements from this wave number, the set of wave numbers, and to avoid double counting, we order them like this. Okay, and then you consider this state. We start from this phi 0 and simply create all these states with wave numbers that we have chosen. Okay, and you apply H. Now, to compute this, we use this commutation relation repeatedly. First of all, I use this commutation relation here for these two guys. And then you switch the order, so H comes here. But here you get this extra thing, so you get this one. But look, so AK is here. Whoops, I made a mistake. Okay, yeah, Dagar should be here. Okay, so a Dagar was here, and it's also here. So this means that this is exactly the same as this one. The same thing with this EK1. And H is now here. So the next thing you want to do is to compute use this commutation relation here. And then you switch, H comes here, and from this you get extra thing like this. So you repeat this many times, and finally H comes to phi 0, but because H phi 0 is 0, the game ends there, and you end up with this. And this is the same thing. So this precisely tells you that this thing is the eigenstate of H, and this is the energy eigenvalue. But this is nothing but the energy eigenvalue we already know. Okay, and we are not going to use this, but you can also sort of diagonalize H by using A Dagar like this. I will show this later in a more general context. Okay, but anyway, we have obtained this energy eigenstate. So energy eigenvalues is given by this, the same as equation 5 in page 3, and energy eigenstates are written like this. More precisely, this is by using this psi wave function psi and C Dagar, it's written like this. Okay, and I argue that this is equivalent to the Slater determinant expression that we have seen in page 3. It's not just immediate to see, but you can find that they are equivalent. But I want to stress that here it's rather tedious to first of all label particles and then change the labels by considering all the n factorial thing and summing up and normalizing. But here you don't do anything. You just pick n these creation operators and apply them to this phi 0. That's it. Okay, and all this symmetry and everything are taken into account. Okay, so that's basically all I wanted to say in this lecture, but let me just discuss general theory corresponding to this. So this is just the same thing, but just consider general free fermion system on any lattice. lambda can be anything, any finite set. Okay, but anyway, in this case, again, we write wave function as a vector like this. And then the single particle Schrödinger equation is again this eigenvalue equation for the hopping matrix T, and it's a hopping matrix is just any Hermitian matrix. But in this case, minus T of uv describes hopping amplitude between V and U, and this represents on-site potential. Okay, and the single particle energy eigenstate is defined like this with some alpha label. This is the number of elements in lambda in this lattice. Okay, and then I can define many-body Hamiltonian again like this, and it looks like this. And this is the creation operator corresponding to this psi alpha. And then, of course, the energy eigenstate. So this is a name of energy eigenstate. Again, is written like this, and it satisfies this. So this is the energy eigenvalue. Everything is the same. And this is the relation that I mentioned before. So since by using this energy eigenstate, this hopping matrix can be written in this form. This is just a standard linear algebra. And then by using this relation and noting that H is BT, and if you go back to the definition of B, and then you can easily show that this is written in this. Whoa, not in this form. I made a mistake. I have to put E alpha here. Okay, you can show you can easily show that this satisfies this. This is a relation that I mentioned here in page 9. Okay, so that's basically all. So here are some remarks and notes. So here we discuss formalism based on the creation annihilation operator, which is sometimes called the second quantization. And I stress that this is a standard description of many particle quantum mechanics used in many different fields. But I really want to stress that this formalism is equivalent to the wave function description that we discussed in the beginning. The wave function description is tedious, but there's nothing special about this formalism. They are exactly equivalent. And in this sense, this terminology, the second quantization, is confusing. And actually the name came from the original confusion in history, I understand. So I think you should better forget about this name, because it suggests that you are doing something. I mean, you had classical system, you quantized it for the first time to get quantum mechanics, and then you're quantizing it for the second time. But it's not the case. This is just equivalent. And if you're interested in this formalism, then I recommend you to look at my lecture note in archive, where I carefully discuss the relation between usual wave function formalism and this creation annihilation operator formalism. And there I sort of derive these canonical anti-commutation relations based on some assumptions. Okay, but of course you don't have to care. If you don't care, that's okay. But here's a good reference. And finally, so this description can be used to describe many different models. So one of them is called the Hubbard model, and I think you have heard of this name. So the Hubbard model is a tight binding model of electrons with on-site interaction. And in this case, electron carries spin. And so in this case, creation annihilation operators is written like this. And here U is lattice site, but sigma denote the electron spin. So U is one of these lattice sites, but in this case, sigma is either up or down. But it's basically the same creation annihilation operators and satisfies the same canonical anti-commutation relation. And then here's the standard Hamiltonian of the Hubbard model. And here you have this hopping part. And now here I assume that hopping is independent of spin. So up spin hops to up spin and down to down. And this is independent of spin. But you can consider a much more complicated model. Okay, and here's the on-site potential. So, but anyway, so this part falls into this general theory of free fermions. So this is a bit complicated, but this is nothing but a free fermion, so it can be written in this way. So if you can diagonalize this matrix T, so if you can solve the single particle problem, then you know everything about this. And this is new. This is the Hubbard interaction, on-site interaction. So here you have sum over all lattice sites U, and here's a product between NU up and NU down. Okay, and the number operator, as you recall, has has eigenvalues 0 or 1. Okay, so it's a product. So this guy can have again eigenvalue 0 or 1, and it has 1 only when both of them are 1. That means that if both upspin electron and downspin electron are at a single site U, then this becomes 1, and usually this is positive, you get extra energy. This is Coulomb repulsive energy. Okay. Now, as I said, it's without this, this is just a free fermion and it's easy in general. And without this, this is super easy. Again, you can think about this and you can easily diagonalize this. But if you have both of them, then this becomes super difficult. And there's no general solution or general method for analyzing this. So you have to have some sort of ad hoc method for treating specific cases. Okay, but you know this becomes super interesting too. And this model, this simple model, is believed to describe various physical phenomena, including, I'm sorry, these are too small to see, many magnetism like ferromagnetism, ferrimagnetism, antiferromagnetism, or the Mott insulator and corresponding metal insulator transition, even superconductivity and more. Okay, but you know it's very difficult to analyze, and so yes, there are many references about this. But if you're interested in, here is my introductory review, basically focused on ferromagnetism in the Hubbard model. But please take a look at this if you're interested in. Okay, so thank you very much for watching. That's all for part 1A.